Hello, y'all. This is Darrell Lee Berry Jr. I'll be reviewing some linear algebra today. First, wanted to show my links to my YouTube, to my X, to my Patreon. Uh, Please support, like, shop, like, subscribe, share, follow Patreon and X, all that good stuff. I'm available to do tutoring. I've tutored up to from the GED level. I'm a learning assistant as well. So I'm familiar with everything up into the lower to intermediate level college. I'm taking higher level physics and math now, so I'm not the best at that. But if you're at calculus, algebra, things like that, physics 1, physics 2, things like that, intro astronomy, stellar astronomy, things like that, I'm happy to tutor. You can go to my website for rates. We could schedule something, or on Patreon, you can sign up there as well. And what I'll be doing today is going through some things on the pad, some things in the book. Basically, I have an exam on Thursday on linear algebra, so I want to do really well on that exam. I'm going to go through the sections, hopefully, that I'm going to be reviewing by then. So basically, I'll be covering in the book sections 1.5, 2.1, 2.2, and 3.2. Since I left off on 1.5 on the last video I did, I'm actually going to start with 2.1. So I'll go 2.1, 2.2, 3.2, and then back to 1.5. So the plan is to go through those by Thursday, by test time. So I'll probably be doing, you know, an hour here, an hour there, or two at various times until that time, as much as I can, to try to get through all the sessions by then. And hopefully, I'll have enough time to do some problems on Thursday, maybe Thursday afternoon, like let's say starting at around noon, something like that, or some problems. So we'll see how it goes, and we'll see how far I get tonight. So I'll go ahead and start with chapter 2. We'll go straight to 2.1. So here's the book, Linear Algebra Geometric Approach. And what I shall do, I'll probably stick with mostly the share view, unless there's something very pertinent that I share on the screen. And with the book, but I'll probably stick with this view here, and we'll go ahead and get it started. So chapter 2, saying is about matrix algebra. Size of the window here, fit to width, and actually, I think I have enough space. Let me see. Yeah, so everything seems okay. So this is where we at. In the previous chapter, we introduced matrices as a shorthand for representing systems of linear equations. Right? Okay. So matrices are shorthand for systems of equations. Now we will see that matrices have a life of their own, first algebraically and then geometrically. The crucial new ingredient is to interpret an m by n matrix as a special sort of function that assigns to each vector x and Rn a product. Okay, so we're going to look at a matrix, say matrix A, as a special sort of function that assigns vector A is a matrix, X is R in Rn, and the matrix is m by n. This is an Rn. So AX equals is in Rn. B and B is in Rn. And this will be because m by n times that's in Rn, so it's n by something, doesn't matter. And oops, and this Rm. So this is going to be m by something, but since m is the first number, that's the row, so that means B has that many rows. 1, 2, m, which means that it's in Rm. So A is a matrix that turns a vector in Rn to a vector in Rm. So this is leading to transforms. So what's going on here? I have here A, an m by n matrix in this example, is a matrix that transforms a vector in Rn to a vector in Rm, right? Which is chapter 2. Right? Matrix operations. And let me plug in my head really fast. Point 1, matrix operations. So recall that an MN matrix A is a rectangular array of M times n real numbers. Does it make sense? So you have A equals A11, A12, AM1, and then the last where you have A1N, A A A1N, oh, that's what I messed up on. It should be 2-1. A2N and AMN. So you have M rows times N columns equals MN numbers. That's what they're saying. Where Aij represents the entry in the ith row and jth column. So we always know that the first number is a row, the second one is a column. Recall that two M by N matrices A and B are equal if Aij equals ABij for all I equals 1 through M and J equals 1 through N. So that's simple enough. If every single number is the same in every single spot, the same spot in different matrices, then it's the same matrix. We take this opportunity to warn our readers that the word if is ordinarily used in mathematical definitions, even though it should be the phrase if and only if.
That is, even though we don't say so, we intend it to be understood that, for example, in this case, if A equals B, then Aij equals Bij for all Ij. Be warned. This custom applies only to definitions, not to propositions and theorems. See the earlier discussions of if and only if on page 21. So that's confusing. So in definitions, if means if and only if. Definitions only. And if and only if is two ifs. So definitions only, if equals if and only if. Everything else then it's still specific. So if we take out these rows, it says A has these rows. So A row 1 equals A11 all the way to A1n. A2 equals A21 all the way down to A2n, and so forth. So these are row vectors. So if it's a capital letter, it's a row vector. So lowercase, column vector, capital, row vector. And notice that in the book, they have it capitalized. So if it's capitalized, that means there's an arrow over it. And notice for the matrix, it's not capitalized. So if it's capitalized, that means it's a vector of some kind. If it's not capitalized, well, I'm sorry, if it's not bold, I meant to say, both of them are capitalized. I meant to say this one is bold, so it's a vector, and this one is not bold, so it's a matrix. So if it's bold, capital letter is a vector. If it's non-bold, capital letter, it's a matrix. And if it's bold, capital letter, it's a horizontal or row vector. If it's a lowercase bold, it's a vertical or matrix vector or column vector. For the column vectors, I'll put those in green. We have A equals A11, A21, and AM1, and so on and so forth. All right, so that's easy enough. And that's A1. So that's column 1. And that means that AN, column N, equals A1N all the way down to AMN. Denote by 0 to 0 matrix, the M by N matrix, all of you. It says we denote by, is that an O? I guess that's a italics type O. We denote by, okay, I guess that's just an italics, some type of italics O. I'll go back to the pad screen. We denote by O the 0 matrix, the N matrix, all of whose entries are 0. So we'll say this weird looking O equals all zeros. I'll just put 1 0 there. We also introduced the notation crazy M by N, for the set of all M by N matrices, okay? For future reference, we call the matrix square if M equals N.
In this case, the square matrix, we refer to the entries I equals 1 through n as diagonal entries. Right? That makes sense. It goes all the way to A66 or whatever the same number will be. So let's really look at these definitions here. Definitions, right? So it says, let A be a n by n matrix. So that means a square matrix with entries Aij for I equals 1 through n and j equals 1 through n. We call A diagonal if every non-diagonal entry is 0. I.e., if Aij equals 0 whenever I equals not j. Okay, so 1, A is diagonal if all non-diagonal entries are 0. So essentially, that's the reduced row echelon form. If you have reduced row echelon form, well, technically, I guess you could have any number. So I guess technically that's not really reduced row echelon if you have something other than ones, understanding. But if you have only numbers in the diagonal and 0 everywhere else, it's diagonal, which makes sense. 2, we call it A is upper triangle if all entries below the diagonal are 0. Right? If I equals 0, wherever I is greater than j, which means for the rows greater than, okay? So we have a matrix down here, I is greater than j, and down and up here, I is less than j. Because we only on the first row, for instance, but we will be here on the 10th column, what have you. Remember, the second letter is always the column. And 3, we call a lower triangle. A is lower triangle. So this is really just definitions. I thought they were going to give us some match, uh, whatever. If all the entries above diagonal, that means that I is I greater than j, or numbers in I are less than j are 0. Let's now consider various algebraic operations we could perform on matrices. Given an m by n matrix A, the simplest algebraic manipulation is to multiply every entry of A by a real number C, scalar multiplication. They're just saying CA. If A is the matrix with entries Aij, then CA is the matrix whose entries are CAIJ. All right, that's easy enough. Don't even write that. Next comes the addition of matrices. Given m n matrices A and B, we define their sum entry by entry. in symbols when A equals that and B equals that. We define A plus B. It's easy enough. You just add related columns just like vectors. Easy enough. It is important to understand that when we refer to the set of all m by n matrices, squiggly m by n, we have not specified a positive integer m and n. It can be chosen arbitrarily. However, when we say that A, B is in the set of all m by n, we mean that A, B must have the same shape, i.e. the same number of rows and the same number of columns. So here's a scalar example. C is -2. So CA is multiply everything by -2, A plus B, just add them together, easy enough. Neither the sum A plus C nor B plus C makes sense because C has a different shape from A and B. So you can only add them when uh, the rows and columns match. We leave it to the reader to check that scalar multiplication of matrices and matrix addition satisfy the same list of properties we gave in exercise 1.128 for scalar multiplication of vectors and vector addition. We list them here for reference. So proposition 1, let A, B, and C all be m by n matrices. Let C and D be real. So we'll call this proposition 1.1 as the book does. So 1, A plus B equals B plus A. 2, A plus B plus C equals A plus B plus C. That's right. The squiggly one means that everything is 0. So 0 plus A equals A. 4, there is a matrix minus A, so that A plus minus A equals 0. Easy enough. One moment.
Here's a matrix, right? 0, 5, C, D, A equals C, D, A. 6, C, A plus B equals C, A plus C, B. 7, C plus D, A equals C, A plus C plus D, A. And 8, 1, A equals A. Proof left to the reader in exercise 3. Okay.
Okay.
To
To
understand
understand
these
these
properties,
properties,
one
one
must
must
simply
simply
examine the
examine the
corresponding
corresponding
entries
entries
of
of
the
the
appropriate
appropriate
matrices
matrices
and
and
use the
use the
irregular
irregular
properties
properties
of
of
real
real
number to
numbers to
see
see
why
why
they
they
are
are
equal.
equal.
A
A
more
more
elegant
elegant
approach
approach
is the
is the
following.
following.
We
We
can
can
encode
encode
an M
M
by
by
N
N
matrix
matrix
as a
as a
vector
vector
in
in
R
R
and
and
N,
N.
right?
Right?
We
We
can
can
encode
encode an
an
m
m
by
by
n
n
matrix
matrix
as a
as a
vector
vector
in
in
Rmn,
Rmn,
for
for
example.
example.
All right,
Right,
so let's
so let's
look
look
at
at this.
this. So they
So they
give a
give a
matrix
matrix
that's
that's
in
in
3,
3,
2,
2,
3
3
rows,
rows,
2
2
columns.
columns.
Oh, I
Oh, I
see.
see.
So they're
So they're
saying the
saying the
vector is
vector is
R6.
R6.
So they're
So they're
saying
saying
that
that
a
a
matrix
matrix
A
A
is
is
m
m
by
by
n.
n.
So
So
that's
that's
similar
similar
to
to
a
a
vector in
vector in
R6.
R6.
So
So
A,
A,
B,
B,
C,
C,
D,
D,
E,
E,
F
F
is
is
just
just
like
like
A,
A,
B,
B,
C,
C,
D,
D,
E,
E,
F.
F.
So
So
this
this
is
is
2
2
by
by
3,
3,
and
and
this
this
is
is
R.
R
2
2
times
times
3
3
equals
equals
R6.
R6.
And it's
It's
written
written
just
just
like
like
that,
that,
straight
straight
down the
down the
line.
line.
It'll
It'll
go
go
straight
straight
across
across
uh,
uh,
this
this
first,
first,
this
this
second,
second,
straight
straight
across
across
the
the
rows.
rows.
You can
You can
check
check
that
that
scalar
scalar
multiplication
multiplication
and
and
addition of
addition of
matrices
matrices
correspond
correspond
exactly
exactly
to
to
scalar
scalar
multiplication
multiplication
and
and
addition of
addition of
vectors.
vectors.
We will
We will
make
make
this
this
concept
concept
more
more
precise in
precise in
section
section
6 of
6 of
chapter
chapter
3.
3.
All right,
Right.
makes
Makes
sense.
sense.
Basically,
Basically,
a
a
matrix is
matrix
a
is a
bunch of
bunch of
vectors.
vectors.
The
The
real
real
power of
power of
matrices
matrices
comes
comes
from the
from the
operation
operation
of
of
matrix
matrix
multiplication.
multiplication.
Okay?
Okay?
Just
Just
as
as
we
we
can
can
compute
compute
a
a
dot
dot
product of
product of
two
two
vectors in
vectors in
Rn,
Rn,
ending
ending
up
up
with a
with a
scalar,
scalar,
we
we
shall
shall
see
see
that we
that we
can
can
multiply
multiply
matrices
matrices
of
of
appropriate
appropriate
shapes.
shapes.
M
M
dot
dot
n
n
times
times
n
n
by
by
p
p
is
is
m
m
by
by
p.
p.
In
In
particular,
particular,
when
when
m
m
equals
equals
n
n
equals
equals
p,
p,
so that
so
our
that our
matrix is a
matrices are
square
square
and
and
of
of
the
the
same
same
size,
size,
but
but
we
we
have
are
combined
combining
two
two
n
n
by
by
n
n
matrices
matrices
to
to
obtain
obtain
another
another
n
n
by
by
n
n
matrix.
matrix.
Right, so
Right, so
this one
this one
seems
seems
important.
important.
So I
So
may
I may
not be
not
able
be
to
able to
fit
fit
this in
this
the
in the
screen
screen
like I
like I
want.
want.
So
So
I'll
I'll
just
just
write
write
this one
this one
out.
out.
We
We
have
have
definition.
definition.
Let
Let
A
A
be
be
an
an
m
m
by
by
n
n
matrix,
matrix,
and
and
B
B
an
an
n
n
by
by
p
p
matrix.
matrix.
AB
AB
equals
equals
C,
C,
which
which
is
is
a
an
m
m
by
by
p
p
matrix.
matrix.
So
So
these
these
two in
two
the
in the
middle
middle
have
have
to
to
match,
match,
and
and
then
then
whatever's on
whatever's
the
on the
outside
outside
becomes the
becomes the
U
U
matrix.
matrix.
So
So
A
A
I
I
one
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 J.
J.
I
I
see.
see.
And the
And the
same
same
thing
thing
happens
happens
with
with
the
the
numbers on
numbers
the
on the
inside.
inside.
You
You
have
have
column
column
one,
one,
row
row
one.
one.
It's
It's
going
going
to
to
add
add
with,
with,
these
these
multiply
multiply
with
with
row
row
one,
one,
column
column
J.
J.
Okay.
So
So
basically
basically
the
the
same
same
uh,
uh,
format
format
happens
happens
with the
with the
numbers.
numbers.
The
The
inner
inner
numbers
numbers
have to
have
be
to
the
be the
same.
same.
So
So
for
for
instance, the
instance, the
columns
columns
that
that
go
go
together
together
will
will
be
be
A11
A11
and
and
B1P,
B1P
so
so
that
that
you
you
get
get
C1P,
C1P,
just
just
like
like
how
how
the
the
final
final
answer
answer
must
must
be.
be.
The
The
things on
things
the
on the
outside
outside
have
have
to
to
match.
match.
It
It
makes
makes
sense.
sense.
That
That
is the
is the
dot
dot
product
product
of
of
the
the
ith
ith
row
row
of
of
A
A and the
and the
jth
jth column
column
vector
vector
of
of
B,
B,
both of
both of
which are
which are
vectors in
vectors in
Rn.
Rn.
Okay,
Okay,
that
that
makes
makes
sense.
sense.
We
We
reiterated
reiterated
that in
that in
order
order
for the
for the
product
product
AB to
AB
be
to be
defined,
defined,
the
the
number of
number of
columns
columns
of
of
A
A
must
must
equal
equal
the
the
number of
number of
rows
rows
in
in
B.
B.
And that's
And that's
because
because
basically
basically
this is
this is
going to
going to
come
come
in
in
dot
dot
product
product
down
down
all
all
of
of
the
the
columns.
columns.
These are
These
all
are
of
all
the
of the
rows.
rows.
It's
It's
going to
going to
come in
come in
dot
dot
product
product
down
down
all the
all the
rows.
rows.
Recall that
Recall
in
that in
section
section
4 of
4 of
chapter
chapter
1,
1,
we
we
defined the
defined the
product of
product
an
of an
n
n
by
by
n
n
matrix
matrix
A
A
with a
with a
vector
vector
v
V
in
and
Rn.
Rn.
So
So
notice the
notice the
vector
vector
that's
that's
being
being
multiplied
multiplied
has to
has to
be
be
the
the
in the
in the
space
space
that's the
that's the
second
second
number
number
of the
of the
matrix.
matrix.
The
The
definition we
definition we
just
just
gave
gave
generalizes
generalizes
that
that
if
if
we
we
think
think
of an
of an
n
n
by
by
p
p
matrix
matrix
B
B
as a
as a
collection of
collection of
p
p
column
column
vectors,
vectors,
in
in
particular the
particular the
j
j
column of
column of
AB
AB
is
is
the
the
product
product
of
of
A
A
with the
with the
j
j
column of
column of
vector
vector
B.
B.
The
The
j
j
column
column
of
of
vector
vector
AB
AB
is the
is the
product of
product of
A
A
with the
with the
j
j
column
column
vector
vector
of
of
B.
B.
Right?
Right?
So
So
that
that
whole
whole
column
column
dot
dot
products
products
down and
down and
becomes
becomes
that
that
column.
column.
Right?
Right?
Let's
Let's
do
do
this
this
example.
example.
Example
Example
2.
2.
Note
Note
that
that
this
this
definition
definition
is
is
compatible
compatible
with
with
our
our
definition
definition
from
from
chapter
chapter
1
1
of
of
the
the
multiplication
multiplication
of
of
an
the
n
n
by
by
n
n
matrix
matrix
with a
with a
column
column
vector
vector
in
in
Rn,
Rn,
an
an
n by
n by
1
1
matrix.
matrix.
For
For
example,
example,
A
8
equals
equals
1,
1,
2,
2,
1,
1,
3,
3,
negative
negative
1,
1,
1.
1.
X
X
equals
equals
4,
4,
negative
negative
1.
1.
B
B
equals
equals
4,
4,
1,
1,
0,
0,
negative
negative
2
2
going
going
across the
across the
row,
row.
negative
Negative
1,
1,
1,
1,
5,
5,
1
1
across the
across the
second
second
row.
row.
So
So
that
that
means
means
that
that
AX
AX
equals
equals
1,
1,
2,
2,
1,
1,
3,
3,
negative
negative
1,
1,
1,
1,
4,
4,
1
1
equals
equals
4,
4,
1,
1,
2,
2,
1.
1.
So
So
this
this
is
is
a
a
3
3
by
by
2
2
and
and
a
a
2
2
by
by
1.
1.
So you
So
know
you
this
know this
has to
has to
be a
be a
3
3
by
by
1.
1.
So we
So
know
then
we're
we're
going to
going to
have
have
to
to
add
add
this.
this.
So
So
1,
1,
3,
3,
negative
negative
1,
1,
1.
1.
So
So
that
that
equals
equals
4,
4,
8,
8,
4
4
plus
plus
3,
3,
negative
negative
1,
1,
1.
1.
So that
So that
equals
equals
7,
7,
7,
7,
5.
5.
And
And
that is
this
a
is a
3
3
by
by
1.
1.
This
This
whole
whole
thing is
thing
a
is a
3
3
by
by
1.
1.
Well,
Well,
did
did
I
I
do it
do it
correctly?
correctly?
Let's
Let's
see.
see.
Oh, I left off a
Off a
negative.
So
So
this
it's
is
a
a
negative
negative
1.
1.
That one
One
negative
negative
changes
changes
everything.
everything.
This would
This
be
would be
negative,
negative,
positive,
positive,
negative.
negative.
So that'll
That'll
be
be
1,
1,
9,
9,
and
and
3.
3.
Right?
Right?
Watch
Watch
those
those
negatives.
negatives.
They're major.
Major.
So
So
that's
that's
a good
good
reminder. And
And
AB,
AB,
that's
that's
going
going
to
to
equal
equal.
So we know that
That
this
this
is
is
a
a
3
3
by
by
2,
2,
and
and
this
this
is
is
a
a
2
2
by
by
4.
4.
So we
So we
know
know
we
we
need
need
a
a
3
3
by
by
4.
4.
So
So
this
this
is
is
going
going
to
to
be
be
4,
4,
1,
1,
2,
2,
1
1
plus
plus
or
or
minus
minus
3
3
negative
negative
1,
1,
1.
1.
That's
That's
one
one
column.
column.
And
And
then
then
1,
1,
2,
2,
1
1
plus
plus
3
3
negative
negative
1,
1,
1.
1.
It's the
The
second
second
column.
column.
And
And
then
then
15
15
negative
negative
5,
5,
5.
5.
It's
It's
the
the
third
third
column.
column.
It's a
It's a
zero
0
number,
number,
thankfully.
thankfully.
We
We
have
have
negative
negative
2,
2,
negative
negative
4,
4,
negative
negative
2
2,
plus
plus
3,
3,
negative
negative
1,
1,
and
and
1.
1.
So
So
that's
that's
going
going
to
to
be
be
4
4
plus
plus
3,
3,
7,
7,
8
8
plus
plus
1,
1,
9,
9,
1
1
minus
minus
1,
1,
0,
0,
1
1
plus
plus
3,
3,
4,
4,
2
2
minus
minus
1,
1,
1,
1,
1
1
plus
plus
1,
1,
2,
2,
15,
15,
negative
negative
5,
5,
5,
5,
and
and
negative
negative
2
2
plus
plus
3,
3,
1,
1,
negative
negative
5,
5,
and
and
negative
negative
1.
1,
All right.
right?
So it
It
looks
looks
like
like
I
I
messed
messed
up
up
on
on
one
one
column.
column.
I
I
have the
have the
4, 1, 2,
4,
1,
1,
negative
negative
5,
5,
negative
negative
1,
1,
15,
15,
negative
negative
5,
5,
5.
5.
Let's see
Let's
what
see
I
what I
did
did
on
on
this
this
first
first
one
one
here.
here.
I must have
Must have
dropped a
dropped a
negative
negative
again.
again.
Oh,
Oh,
yep,
yep,
it's a
it's a
negative
negative
3.
3.
This
This
would
would
be
be
4
4
minus
minus
3 is
3 is
1.
1.
8
8
plus
plus
1
1
is
is
9.
9.
And
And
4
4
minus
minus
1
1
is
is
3.
3.
Gotta
Gotta
watch
watch
those
those
negatives.
negatives.
All right,
Right,
there we
there we
go.
go.
Notice
Notice
also
also
that the
that the
product
product
BA
BA
does
does
not
not
make
make
sense.
sense.
B
B
is a
is a
2
2
by
by
4,
4,
and
and
A
A
is a
is a
3
3
by
by
2,
2,
and
and
4
4
equals
equals
not
not
3.
3.
BA. So
So
what
what
that
that
means
means
is
is
that
that
AB
AB
equals
equals
not
not
BA
BA
when
when
A
A
and
and
B are
B are
matrices.
matrices.
So we
So
have
we
to
have to
keep
keep
that
that
in
in
mind.
mind.
Might
Might
even
even
be
be
possible.
possible.
The
The
preceding
preceding
example
example
brings
brings
out an
out an
important
important
point
point
about the
about the
nature
nature
of
of
matrix
matrix
multiplication.
multiplication.
It can
It can
happen
happen
that the
that the
matrix
matrix
product
product
AB
AB
is
is
defined
defined
and the
and the
product
product
BA
BA
is
is
not.
not.
Now, if
Now, if
A
A
is an
is an
n
n
by
by
n
n
matrix
matrix
and
and
B
B
is an
is an
n
n
by
by
m
m
matrix,
matrix,
then
then
both
both
products
products
A, B,
A, B,
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 A
A
make
make
sense.
sense.
AB
AB
is
is
an
an
n
n
by
by
m
m
and
and
BA
BA
is an
is an
n
n
by
by
n.
n.
Notice
Notice
that
that
these are
these are
both
both
square
square
matrices,
matrices,
but of
but of
different
different
sizes.
sizes.
That's
Interesting.
interesting. AB
AB
equals
equals
not
not
BA.
BA.
So
So
this is a
this is a
good
good
place to
place to
pause
pause
for
for
now.
now.
I'll
I'll
just
just
take a
take a
break
break
and
and
I'll
I'll
come
come
back
back
in
in
15 to
15 to
20
20
minutes,
minutes,
something
something
like
like
that,
that,
for
for
part
part
2.
2.
So
So
30
30
minutes
minutes
at
at
the
the
max.
max.
I'll
I'll
be
be
back
back
and
and
we'll
we'll
keep it
keep it
going.
going.